Hello. So this week we're going to take a look at how transforms work in Unity. So the first question is, what is a transform? A transform is just a component that every game object in Unity has to have, and which allows us to define and manipulate the spatial properties of that object. So let me show you an example. Here I have an empty scene in Unity. I'm going to go ahead and create a new game object. So let's create a cube. Right, so we can see a few things have happened. The cube that I've just created has appeared here in the scene view. It's also appeared over here in the hierarchy. And because I've got the cube selected, we can see that the inspector over here shows us the various components that game object has. So this is the transform component over here. So we can see that it defines basically three things. It defines the position of the cube, its rotation, and its scale. For now, we're just going to start looking at what we mean by position. So you can see here, this is a 3D vector with X, Y, and Z components. At the moment they're all set to 0. But if I go into the scene here and start moving this cube around, and I'm using the move tool here, select move up here. If I move it around, you can see that the vector components in the inspector are changing as well, right? So there we go, I'm moving it, changing its Z value. Let's go ahead and change its Y value and its X value, right? So over here, we've moved the position. And likewise, I can change these values in the inspector. So if I change the X component to 10, then there we go, it's moved the cube within the scene. So the transform component gives us a way to move and rotate game objects in our game. And most importantly, it allows us to actually write code that can change those values during the game itself. And that is going to turn out to be incredibly useful. For our game to change and react to the position of game objects, we're going to need to work with vectors. Now, Unity gives us a couple of useful structures for doing this. Vector 2 for 2D vectors and Vector 3 for 3D. And whenever you're writing C# scripts, I recommend you have relevant documentation to hand. And you can see there's the URL for the Vector 2 documentation. Okay, so next we're going to recap some basic vector maths and take a look at how we work with vectors in C# code. I'm sure a lot of you will remember your vector maths from school, so if you're already comfortable with operations like dot product and cross product, feel free to skip on to the next video. Let's remind ourselves of some basic vector concepts starting in 2 dimensions. Recall that a vector is made up of a magnitude and a direction. So in 2 dimensions, we can define this as a pair of components, x and y. And if we imagine the vector starting at the origin, then x and y are basically how far it extends along each of the axes. So in Unity, we're going to use vectors for a number of purposes. Or we can represent a point in space, so that could be the position of an object in a scene. It could be a relative position, so starting at one object, a vector could describe the displacement we take going from that object to another object. We can also use it for concepts where there's a quantity and a direction. So the velocity of an object could be stored as a vector, and likewise the acceleration acting on an object or a force. So Unity provides a struct called vector2, which lets us represent 2-dimensional vectors. Struct you can think of as a kind of a value type like int, but one that has some features of a class. So for example, a struct can have properties. It's kind of like a cut down version of an object. So the vector2 struct we can define using the new keyword. We can create a new struct, vec, and give it the x and y values when we create it. And then we can use the dot notation .x and .y to retrieve the x and y components. So the magnitude of a vector is basically its length, and in vector 2 we have a magnitude property which we can use to give us that length. So that's useful, for example, if we have a vector representing displacement of two objects, then the magnitude is going to tell us how far apart they are in space. And if we have a vector, say, representing the velocity of an object, then the magnitude is going to be able to give us the speed. Sometimes we don't care about the length or magnitude of a vector, but we just care about its direction. So in those cases, we often use what's called a unit vector. That's a vector which has a length of 1. 1 indicating that we don't really care how long it is, it's just giving us a direction in space. So you can take any vector and divide it by its length in order to create a unit vector which is pointing in the same direction. This process is called normalization, or normalizing a vector. And we can use the normalize method on vector 2 in order to get the unit vector for any given vector. We could also use a read-only property called normalize to get the same value. Now, vector 2 supports all the standard arithmetic operations, basic vector maths. So if we have two vectors A and B, we can talk about adding them together to get their sum, or subtracting them, multiplying them, or dividing them. So let's think why we might want to do that. Well, if we've got an object at position A, then we might want to teleport it by some displacement vector. So if we have a displacement B, then adding that displacement to A is going to give us the new position of the object. Or you could think about A and B both being forces which are acting on an object. And we could, say, have a force of gravity and the force of some explosion, both being separately calculated. If we want to get the overall combined force, then we can add those two vectors together. Subtraction of vectors is really useful if we're thinking about the vector from B to A, then we can use A minus B to calculate that. So, if, for example, we're firing a missile from B, then that vector A minus B is going to give us a heading towards the position A, and its length is going to be how far that missile is going to have to travel. So in situations where we've got a vector heading in the right direction, but we want to vary its length in some way, then we can use a multiplication or division by some value n here to do that. So, for example, if we wanted a force which was acting on an object to get stronger or weaker in response to some player input, then we could multiply or divide that force vector by another value. Dot product is another vector operation which comes in very handy in game development. So we write it a dot b, and that's how we compute it using this equation. So we take the magnitude of A, multiply it by the magnitude of B, and that again by the cosine of the angle between them. So this returns a scalar value, a number, and you can think of that number as measuring something about the similarity between those two vectors. And that turns out to be extraordinarily useful when we want to compare vectors in various ways, and also useful in that it's very efficient to calculate, so it's something we can do a lot of during our game. So if we've got a normalized vector A, and we take the dot product with another, then we can think about it in this term. So we can think about the dot product of A and B being the amount that B is extending in the direction of that normalized vector. So if we have two normalized vectors, if A and B are normalized, we can actually use this to compare their kind of relative positions. So if A and B are pointing in the same direction and they're both normalized, then the dot product is going to be 1. If they're pointing in opposite directions, then it's going to be -1. And as we change the relationship between the two, say rotate B, so it's going from completely in the same direction to the completely opposite direction, the dot product is going to vary. Right? So we can take the dot product to compare how the relative orientations of those two vectors. And if there's a zero dot product, that means the two vectors are at right angles. So here's one use of a dot product in a bit of C# code. So we're basically taking a vector A and a vector B, taking the dot product, and then using the arc cosine function to convert that to the angle between those two. So we're taking the dot product which represents the relative orientations and using arc cosine to convert that to an actual angle between those two vectors. So that allows us to say, for example, if we wanted to rotate A so it was facing the same direction of B, we now know how far we need to rotate it. Another application of the dot product is to say, if we have a player and some other object in the scene, we can ask, is the object in front of or behind the player? What we can do there is just take the vector which describes going from the player to the object, and take a unit vector, which is the direction the player is facing, and take the dot product of those two vectors, both normalized. In that case, that's going to describe whether the player is facing towards or away from the object. Another application of dot product in games is when we're interested in how fast an object is moving in a particular direction. So it's perhaps got a velocity along a track, but it's also moving side to side on that track. So its velocity is going to be perfectly aligned with the track. But we want to know how fast it's actually moving along the track. What we can do there is take its velocity, which could be facing in a number of different directions, and take a unit vector, which describes the direction of forward motion along the track. If we take the dot product of those two, then we get the speed it's moving along the track, independent of its actual speed, which includes side-to-side movement. Up to this point, we've only considered 2D vectors, but these ideas generalize to 3D quite straightforwardly in Unity. So we have the vector3 struct, and that supports the same kind of operations we've seen so far. So arithmetic operations like addition and subtraction, dot product and normalization. Something that you get in 3D which you don't get in 2D is the idea of a cross product. So this is another operation over two vectors, but they have to be 3D vectors because it's describing something which is inherently 3D. So when we take the cross product of A and B, we're getting back another vector, and that's a unit vector. It's going to have of length 1. So we can think of that vector pointing out of the plane defined by A and B. So if you imagine A and B being two vectors in space, put them in a common origin starting at the same point, and you can think of a bit of paper which they both lie along. That's the plane which is defined by those two vectors. So the cross product vector is pointing at right angles out of that plane. And if they have the same direction, or one of them has zero length, then you get zero vector returned as the cross product. So the obvious question here is, if you take the cross product, it's pointing out of the plane defined by two vectors. Well, which way is it pointing? So there's something called the right-hand rule, which can help you work this stuff out. And you'll be sitting there playing with your right hand, trying to work out which way your object should be moving through your Unity scene. So if we take two vectors, u and v, think about u basically running along your arm, and v is coming at right angles out of your palm. Now, if we take the cross product u times v, then your thumb is pointing in the direction of that cross product. If we take the opposite cross product, v times u, then the cross product is pointing the opposite direction, pointing away from the red line there in the diagram. So one way that cross products can be used in game development is to find normals, right? So a normal is just a fancy word for the vector I've just described, the vector which comes out of a plane at right angles. So let's look at this bit of code here. It's taking three vectors A, B, and C. You can think of those as three positions in a Unity scene. And then we're looking at the vector that goes from A to C, and the vector that goes from A to B. So A is a common origin, and side 1 and side 2 are these two vectors coming out of that point A. So what we're defining there is a plane which goes through that point A and runs along those two sides. So the normal of that plane is the vector which is coming out at right angles, and we can use the cross product to calculate that in a very straightforward way. So these kind of calculations are used all the time in game development in order to calculate normals for doing things like collisions in physics engines and for calculating lighting. So that happens all the time in games, but in Unity you don't have to worry about that because physics and lighting are typically handled by parts of the Unity engine that you're not writing code for yourself. So a more kind of day-to-day use of the cross product for you would be something like trying to work out how you should be rotating something in 3D space. So imagine we've got this little tank here that's pointing in the direction A, given by one vector. And we have another vector B, which describes the way it should be pointing, right? It needs to point its gun in B so it can shoot something. So we know that we need to rotate the vector A in 3D space to the vector B. But the question there is, how do we rotate it? Now, rotation is going to be defined by another axis, right? We could call that C. C is basically the axis in which we're doing the rotation around. So C here, we can think about as coming straight out the top of the tank. So in order to calculate what C is, given that we know A and B, we can take the cross product, right? So remember the right-hand rule. So I'm going to put my arm so it's lined up along B, and then we've got A coming out of my palm, then C is going to be pointing the direction of my thumb. Okay, so in that case, we know it's B times A. That's the cross product we need to calculate C. So we've looked at various vector operations which Unity lets us do, and we've talked a bit about how they might be useful in game development. So if you're interested in reading more on this, I highly recommend the Unity Manual's Vector Cookbook, which can be found at the URL there.